5.5 Complex Eigenvalues. All right. Since the characteristic equation of an n... Wait, let me make sure everything's right. Test. All right. And... Okay. Since the characteristic equation of an n by n matrix involves a polynomial of degree n, the equation always has exactly n roots, counting multiplicities, provided that possibly complex roots are included. This section shows that if the characteristic equation of a real matrix A has some complex roots, then these roots provide critical information about A. The key is to let A act on the space Cn of n tuples of complex numbers. Our interest in the complex numbers does not arise from a desire to generalize the results of earlier chapters. Rather, this study of complex eigenvalues is essential in order to uncover hidden information about certain matrices with real entries that arise in a variety of real-life problems. Such problems include many real dynamical systems that involve periodic motion, vibration, or some type of rotation in space. The matrix eigenvector theory, already developed for Rn, applies equally well to Cn. So a complex scalar lambda satisfies the determinant of A minus lambda I equal to 0 if and only if there's a non-zero vector x in Cn such that Ax equals lambda x. We call lambda a complex eigenvalue and x a complex eigenvector corresponding to lambda. If A is equal to 0 minus 1, 1, 0, then the linear transformation A to AX on R2 rotates the plane counterclockwise through a quarter turn. The action of A is periodic since after 4 quarter turns, the vector is backwards started. Obviously, no non-zero vector is mapped into a multiple of itself. Obviously, no non-zero vector is mapped into a multiple of itself. Right. Yeah. So A has no eigenvectors in R2, and hence no real eigenvalues. The characteristic equation is lambda squared plus 1 is equal to 0. The only roots are I and minus I. If we permit A to act on C2, then we see that that I1 is and I minus I1 are eigenvectors corresponding to I and minus I eigenvalues. The method for finding them is discussed here. Okay, so let A be this. Find the eigenvalues of A and find a basis for each eigenspace. Okay, the characteristic equation of A is the determinant of 0.5 minus lambda minus, okay. So you get this characteristic equation from the quadratic formula. You get these eigenvalues. Then you take the first eigenvalue and you construct A minus lambda I. Row reduction of the usual augmented matrix is yo, what's up, bro? What's up, man? I'm kind of tired, dude. I went on this long run yesterday. I feel like I'm kind of out of it. Doing good, though. think it's also gonna add like a big lunch, and I'm like, but I'm good. And you know what I'm realizing? I'm realizing that although I'm gonna have to skip some sections, like 5.5, I'm technically not even really supposed to do because we're not even being assigned it. But it seemed like too important of a section to skip. But my class is gonna end at the end of chapter 6 on orthogonality and least squares. But I'm thinking I should probably just over the summer just finish this book because then I'll say, at least I did one book. At least I've worked through one book. All right. So we get this, we get this. Now we do row. They say, okay, row reduction of the usual augmented matrix is quite unpleasant by hand because of the complex. Because the chapters that I want to get into, I don't know about chapter 8. Chapter 8 might be interesting. But I definitely think chapter 9 would be fun because I've heard all this terminology on linear programming, but I don't really know what that even means. And similarly, Markov chains seem really interesting, so that'll be a fun chapter. Yeah, I'm gonna go. I'm gonna go ahead once the class ends, though. I'm not gonna like. I don't think I'm gonna like try to go ahead while I'm still in the class. I'm just gonna keep at the pace of the class and then try to keep up with 4 or 5 sections, maybe 3 or 4 sections per week. Yeah, probably 3 sections per week would be pretty good. Okay. However, there's a nice observation that really simplifies matters. Since 0.8 minus 0.6 I is an eigenvalue, the system has a non-trivial solution with x1 and x2 possibly complex numbers. Therefore, both equations in 2 determine the same relationship between x1 and x2. And either equation can be used to express one variable in terms of the other. Okay, choosing x2 equal to 5. We get a basis for the eigenspace. Okay, and then we do the other one. One way to see how multiplication by the matrix A in example 2 affects points is to plot an arbitrary individual initial point and then plot successive images of this point under repeated multiplications of A. The smaller dots are locations of x9 to 100. Oh, wow. Of course, figure 1 does not explain why the rotation occurs. The secret to the rotations is hidden in the real and imaginary parts of a complex eigenvector. The complex conjugate of a complex vector in x in Cn is the vector x bar, whose entries are the complex conjugates of the entries in x. The real and imaginary parts of a complex vector are the re and im of x. If x equals Okay. If B is an m by n matrix with possibly complex entries, then B bar denotes the matrix whose entries are the complex conjugates of the entries in B. Let R be a complex number and X be an X any vector. Properties of conjugates for complex numbers carry over to complex matrix algebra. Okay. Eigenvalues and eigenvectors of a real matrix. Let A be an m by n matrix whose entries are real, then wait, what? Oh, because the complex conjugate of a real matrix is itself. If lambda is an eigenvalue in A of A and X is a corresponding eigenvector in Cn, then hence complex conjugate of lambda is also an eigenvalue with X bar a corresponding eigenvector. This shows that when A is real, its complex eigenvalues occur in pairs. Here and elsewhere, when we use the term complex eigenvalue to refer to an eigenvalue, lambda is equal to A plus BI, where B is non-zero. The eigenvalues of a real matrix in example 2 are complex conjugates. The corresponding eigenvectors Okay, that's pretty cool. So you get complex conjugates if it's a real matrix with complex eigenvalues. And that forces that the eigenvectors are also complex pairs or conjugate pairs. Then we see that matrices of this form can be transformed into a composition of a rotation and a scaling. But people that 2 by 2 matrix in theorem 9? What was theorem 9? Oh. Why would they refer to it after? That's weird. Okay. So you let it be the real component on the first column. And the imaginary part of the eigenvector on the second. Okay, from C is equal to P inverse AP. if a real matrix A has one complex, if it's a real 2 by 2 matrix A has one complex eigenvalue, then they're both complex. Because just by direct application of the fact that they need to come in pairs, but why do they need to come in pairs? Because AX equals, yeah, okay. Oh, but this is only true if A is real. That's interesting. Why would the real part be linearly independent from the imaginary part? Let me get some more water. All right. Let A be a real 2 by 2 matrix with complex eigenvalue. An associated eigenvector V in C2. Okay. Um. The phenomenon displayed in... Dude, this is confusing to me, man. Persists in higher dimensions. For instance, if A is a 3x3 matrix with a complex eigenvalue, then there is a plane in R3 on which A acts as a rotation. Whoa. Possibly combined with scaling. Every vector in that plane is rotated into another point on the same plane. We say that the plane is invariant under A. What does that mean? In this context, saying that a subspace is invariant under the linear map A means... Okay, here's the definition. A subset S in Rn is invariant under A... Wait, what? But also, that's true of all subspaces. Wait. Is that true of all subspaces? That's not true of all subspaces. Yeah, so every eigenspace is invariant. Okay, this matrix has eigenvalues 2 complex eigenvalues and 1 real eigenvalue. Any vector W0 in the x1, x2 plane with third coordinate 0 is rotated by A into another point on the plane. I'm gonna go put on some socks and pants. Okay. any vector x0 not in the plane gets scaled. The iterates of the point w0 equal to 2, 0, 0, and but because of the zeros here, there's no interaction really. Man, understanding even just the 3x3 matrix is like pretty hard to do. Okay. All right. So that's cool. All right, what's up with this robot? Oh wait, that's the whole section? Many robots work by rotating at various joints, such as just as matrices with complex eigenvalues rotate in points in space. Figure 6 illustrates a robot arm made using linear transformations, each with a pair of complex eigenvalues. In Project C, at the end of the chapter, you'll be asked to find videos of robots on the web that use rotations. Okay, that's not even that. That's really kind of just hacked in there, isn't it? Show that if A and B are real, then the eigenvalues of A are A plus BI. Okay, so A minus lambda squared plus B squared. A minus lambda all squared is going to be A squared minus 2A lambda plus lambda squared plus, hold on, let's just do this. I think that this will work. If I have at variables A, B, B, then I have A is equal to A minus B, BA, and then I call det on A. It should be, okay, but if I did, um, oh yeah. Okay, so we could let C equal A squared plus B squared, and then do the quadratic formula. All right, let's read through the exercises. Okay, so find the eigenvalues and a basis for each eigenspace. In 7 through 12, use example 6 to list the eigenvalues of A. In each case, the transformation Okay, these I want to do a couple of these just to maybe get it. Hammer at home. I don't have my camera set up, but that's fine. In 13 through 20, find an invertible matrix P and a matrix C such that A is equal to. Okay. We should, yeah, so we should do like two of these, two of these. We'll do one of these just to practice it maybe. An example to solve the first equation in 2. For x2 in terms of x1 and show, and from that produce the eigenvector y. Oh yeah, show that this is a complex multiple. Yeah. We need to do another couple examples of how to do division in complex numbers, because I think what you have to do is you have to, like, if you have like x over a plus bi, you multiply the top and the bottom by the complex conjugate, and then you're going to get a real value on the bottom. I think that's what you have to do. Hey, what's up, bro? Dude, that's so nice, man. Yeah, I'm having a pretty good day. I just like, I feel like sometimes it's hard to get in the zone mathematically. Like, you could be reading the definitions, you could even be doing the problems, but it's almost like you're kind of going through the motions. And it's not like as useful, like, it's not as useful as it could be if you were like in a better state of mind. But I don't know how you can improve it. All right, so for this one, what we're going to do is, I think we just have to show for each of these numbers that this is a complex multiple of V1. Okay, so we're definitely going to do 20. Okay, let me get out my paper. Say. Okay, so which problems did I want to do? I wanted to do, let's say, 1, 7, 9, 13, 15, 21. This is for 5.5. All right. 22. Let A be a complex or real n by n matrix, and let X and Cn be an eigenvector corresponding to an eigenvalue lambda in C. Show that for each non-zero. See, you know what I want to look up? I'm just. In the 18th century, Euler studied the rotational motion of a rigid body and discovered the importance of principal axes. Lagrange realized that the principal axes are the eigenvectors of the inertia matrix. Oh, wow. Oh, that's how it was studied? In the 1700s, no less. In the early 19th century, Cauchy saw how their work could be used to classify quadric surfaces. Oh, that's so sick. I didn't even know about this. Why are there no pictures here? That is so cool, man. Wow, isn't that nice? The picture doesn't even show up. Hermitian is just right. Conjugate transpose. That's what it is. If you have a real n by n matrix with real eigenvalues, what? If you have a real n by n matrix and it has real eigenvalues, then is it guaranteed the eigenvectors are real? What's the proof if so or not? Since lambda is a real eigenvalue, then there exists some possibly complex non-zero vector v. Uh-huh, okay, that's fine, yeah. X plus iy, okay. Because v is not equal to 0, at least one of the x or y is non-zero. Whichever is non-zero. Wait, what? Because v is not equal to 0, at least one x or y is non-zero. Whichever is non-zero. Oh, okay. Um, all right, wait. So let me read this problem again. So A is a complex or real n by n matrix, and let C or let X in Cn be an eigenvector corresponding to an eigenvalue in C. Show that for each non-zero complex scalar lambda, the vector. Okay, if we're just talking about reals, then the geometry just gets so mind-boggling when you're talking about the complex numbers. because this actually is a really good problem, because it's like mu can be complex. So whenever I think about eigenvalues, all I think about is real eigenvalues, where you have a line and A just acts on that line by scaling it. And so it's pretty easy to get in your head what that means. But now, if mu is a complex number, it all comes down to you can't visualize the plane, or you can't visualize C2. Visualizing C2 is basically impossible, because it's like trying to visualize 4 dimensions. Like, where does the imaginary part go? I don't know. Okay, then true falses, we'll do that. I at least want to read the answers to these. The thing is, reading the answers really gives you nothing, so I don't know. Okay. Chapter 7 will focus on matrices A with the property that they're symmetric. Let A be an n by n real matrix with the property that it's symmetric. Let X be any vector in Cn. And let Q equal the equalities below show that Q is a real number. Okay, so we should do this. So Q is a real number by verifying that Q equals Q bar. Okay, so you're allowed to take the complex conjugate of both sides. If something is equal, then its complex conjugate must be equal. That's just they don't even ask you to provide a justification for that. But now this is equal to this, because if you have X transpose, so this is going to be a row vector. I would say because the double complex conjugate, but the thing is, this bar on the top is not just associated to but I think it's because you can split it up. Like, if you have it's based on those identities that they said at the beginning, like this one. RB all complex conjugated is equal to R complex conjugate B complex conjugate. So that's what my justification would be. But I don't know why that's true, like, more deeply than that. Hold on, let me get my. There we go. All right. So, so then what's the next part? So that one we kind of got. Then this equality, what's changing? A is real, so then it's equal to its, so that one's easy. Then this one, That one's interesting. I don't know about that. E. Um. Well, this is just equal to A, and this is this is what we assume to be true. All right, 27 is pretty good. I don't know about all that. 28. Let A be an n by n matrix with a property that's symmetric. Show that if ax equal lambda x for some non-zero vector x in Cn, then in fact lambda is real. Oh my gosh, I'm so sleepy. Lambda is real, and the real part of x is an eigenvector of A. Let A be an n by n matrix with that's symmetric. Okay, so if you have a symmetric real matrix that's square, real, symmetric, and you have some complex eigenvector, then the eigenvalue is real. You're telling me 28 seems crazy. I wouldn't even thought that was true. 29. Let A be a real n by n matrix and let X be a vector in Cn. Yeah, we should show this. I didn't know that this was true. This is only true if it's real. They should also have a part B that says show that it's not true if A is complex, because I'm pretty sure it's not. Let A be a real 2 by 2 matrix with a complex eigenvalue, an associated eigenvector V. Ugh. I'm trying to think. Let's see, if I do this, I just want to test something out. If I have A is equal to rand complex 4 by 4. What? Do I have to do like, how do I get a 4 by 4 matrix of complex numbers? Do I have to do this? Rand complex 64? What? There's no way to get a random complex number? It's weird. You have to do that. Okay. Okay, there we go. Here we have a 4 by 4 where we have complex numbers, and then we have an x, which is equal to this. Now, a times x, yeah, approx a times re. Is re a thing? Re called real? Okay, but if a was real, oh, silly. Oh wait, really? Wait, I think that is true. What? Because if you have, who, I've never ever seen this ligature ever. Is that the right word? No, that's not even the right word. That's not what I'm trying to say. I've never seen that symbol before. What the hell is this thing, man? I'm gonna take a screenshot of that. That thing is weird. Oh, yeah. But I is not a thing. How do you get? Oh, is I? No, but that's not the right I. Complex. I think you just do 0, 1, right? Oh, im. Can I do it 1 im? There we go. Wait. But not true if a complex, right? Oh, I guess it is true. But why though? Why though? All right, let's get back to the book. Um, all right, let's just do the problems. All right, so find the eigenvalues and a basis for each eigenspace. I don't have my camera right now, so I'm just gonna do it by myself. Okay, so I got the characteristic polynomial. So if we have a is equal to 1 minus 2, 1, 3, eigen of a. So if we just, oh wait, you know what? Hold on. How did they do it? Um. Oh yeah, I know. We have to use the quadratic formula, right? So we get minus b, so it's 4 plus or minus square root. All right. So the characteristic polynomial. I'm pretty sure if I do, see, det of a minus lambda, is lambda symbolic? I think it is. But I'm pretty sure that we get, and we do, do we have a factor? But I feel like, is this from symbolics? No, see, that's ridiculous. That's not even what that is. That's factor use Nemo. Why not? I just have an expectation that this will break everything, but we'll see. But also, it seems like even if I have using Nemo, it's not going to do it. That's actually pretty cool. It's not great, but it's pretty cool. Surely this has been improved by now. And we can solve generic yeah, I don't care. So yeah, so let's just find so it's gonna be minus b 16 minus 4ac, which is 20 over 2a, which is 2. Then we get 4 plus or minus the square root of minus 4, which is equal to 2i, right? So it's going to be 4 plus or minus 2i over 2, so it's going to be 2 plus or minus I. Those are the eigenvalues. Was I right? Oh, great. They overload RF. Did this just destroy my whole world? Let's see. Good. Okay, I didn't even actually care about that. Wait, but I did want to factorize this thing. How do I factor? Oh, but it did work. That's cool. Oh, so that code path only gets hit if But why does this look so terrible? It's not even good. That's okay. Doesn't need to be good. All right. Okay, so wait, were we right though? 2 plus or minus m. Okay. Now what are we supposed to do? We're supposed to find the so finding a basis of that eigenspace. It amounts to finding the null space of, so if we took A, wait, so let's just say one of our eigenvalues was, so one of our eigenvalues is, well, let's just do this. We have them right here. So if E dot values 1 is the first eigenvalue. If we did I times this, and then we did A minus, okay, we would get this matrix. Now the null space of that matrix, wait, I thought it was supposed to be the same. Okay, wait, so A minus lambda 1 I is equal to, and it's going to be minus 1 plus m minus 2, 1, and 1 plus 1 m. So this means that minus 1 plus m times x minus 2y is equal to 0, or, and apparently that's the same equation as x plus 1 plus m y. But it's not the same equation, right? Because I thought they said if I don't know if that's true though. So its rows are linearly dependent. Okay. But the eigenbasis I prefer how this thing does everything pretty much. It's pretty much all around better, except it's more annoying to write out the actual matrix. Wait, is the... Okay, wait, hold on. Let me just do this. If the space does have dimension 1, then the eigenvector is the basis of the eigenspace, right? Whoa. No, we never did the practice problem. So we have a minus lambda minus b, a minus lambda. Okay, I got this. Then you find the basis. So you take the first eigenvalue and you solve for the null space. How did they do this? Okay, yeah, we did this. We just did that on Julia. Then we need this to be 0. So from the first row you get So if x equals, if y equals 1, then x equals. Wait, that's weird. Because I had 1/2. Oh, is that what they had? See, that's the crazy thing. That's wild. It's so hard to think that those are scalar multiples of each other, but they are. Oh my goodness. Okay. So, but it was right. All right. I was just being stupid. All right. Okay. Oh wait. Yeah. Problem 7. We have a is equal to root 3, 1, root 3, or 1, root 3. So, so what are we trying to do though? We're trying to. Oh. No, I need to read this again. So then theta is the angle between the positive x-axis and the ray from 0, 0 through AB. Right. So it's going to be sine So then it's going to be the arctangent of root 3 over, so a tan d, wait, no, a tan, there's no a tan d, wait, what? Where the output, yeah, it governs the output, though. So this is going to be 1 over square root 3. Let's do this. Okay, so then we say that theta, or what is it, phi, is equal to 30 degrees. Is it 30 degrees? And then how do we, okay, so then how do we find the, so then R is equal to, so then the R matrix for scaling is A squared plus B squared? Oh, the square root. Okay, so square root of 1 squared plus root 3 squared is equal to 2 is equal to R. So then we have the identity matrix times 2, which is 2, 0, 0, 2 times, and then the rotation itself is going to be, and the eigenvalues of C are this. Then you can also write C as R over R. Oh, right. Okay, yeah. Alright, so here's the final important part. Let P be the 2 by 2 real matrix. I don't know why you do this. This is so weird to me. So you take an eigenvector, then you form this matrix out of its components, and then you This is crazy. What? Oh, but that's only because A actually has these pure rotations. But it's not that all of them are going to be pure rotations. Okay, so here's what I want to know. If we have this A, where's A? Square root 3 minus 1 square root 3. Okay, what I want to know then is if we do, oh shit. Is this gonna work? Oh, I fucking sick of typing, dude. Okay, so but I thought it was a pure. Oh, it's not. This one's not a pure rotation because um some square symbolic set square. Um. So if we take so the thing about this is we do some right. Oh shit. Course the course. Oh wait. Bro, I am not getting anything out of this. Like, what is the matrix? Because this only works for 2 by 2, right? Because you're going to have a n by 2 matrix. So then you have to have a 2. So this thing only works. All right, let's just do the freaking true false. And then we'll end this thing, man. I'm exhausted. I don't know why. Or, well, let's, here. Oh, shit. That's not what I wanted to do. Oh, shit. I'm starting to see it, man. So, wait. So, since it's for each eigenvector that we have a P matrix, then there's like, it's not like when we have real eigenvectors and eigenvalues that just scales it, but it is a rotation plus a scaling. Wait, is it a rotation plus a scaling? Because what the hell does this do? I'm having a very hard time understanding the geometry of these complex eigenvectors and eigenvalues. It seems like we do get we get like two vectors for which we have this decomposition because it's a 2 by 2. I don't know. Let's just see what it says. It's just so complicated. I wish there was more pictures for this stuff. All right, let's just keep going. Wolf. All right, let's just this one is just a matter of dividing out, right? Let's just do true, false. The matrix A, if A is 2 by 2, that's false. So let me just do that. 23, false. 24. I don't think that that's true. That's only if the eigenvalues norm is 1. Otherwise, it's going to spiral. The matrix A always has 2 eigenvalues, but sometimes they have algebraic multiplicity 2 or complex numbers. Yeah, that's true. The matrix A has 2 complex eigenvalues. Then it also has 2 linearly independent real eigenvectors. What? I don't know. Because why would you? Matrix A always has 2 eigenvalues, but some doesn't. Okay, but then this one. Okay. All right, that's it. I'm freaking